Log on, tune in, find out. Another good idea from Cambridge.
Yeah, I would like to thank the organizers for inviting me to give a talk. So I'm going to speak on joint work with Matthew Clark. And this is the title. So about 8 years ago, I wrote a paper on applications of Cam-Rousseau theory to nilpotent orbits. And that worked quite well in good characteristic. So one could recover Pomeraniec theorem in a case-free fashion. But I always felt that there was some unfinished business here because somehow when I learned literature better, I realized that what Hesselink did actually provides some case-free approach, well, in any characteristic. So it's basically all things that remain the same in any characteristic somehow come from these stratifications, and then the difficult part starts when you look at the strata in some particular characteristics. And so I also learned some point about paper of Seshadri, which was relevant to what we did. And another point was work of Lustig, who introduced very interesting notion of unipotent and nilpotent pieces and singled out some properties which he called P1, P5. And these properties, P1, P5, don't depend on field at all. So they just, well, he predicted that they should hold always. And this somehow was, well, relevant to what I thought about it. And so we decided to look again at this. So let me first remind you some notions of Cam-Rousseau theory, which is basically invariant theory. Let me first start, well, K will be an algebraically closed field. Of characteristic, any characteristic. And sometimes I will specialize to either the closure of Fp or a complex number. So, and I will somehow switch between these two. Now G is connected, reductive algebraic group over K, and so C is a maximal torus. And then we will have sigma is the root system, and pi is a set of simple roots. Now, what one starts is one starts introducing a set of y of g. It's the set of all rational homomorphism from the group K cross, multiplicative algebraic group, to all homomorphisms lambda. They are denoted by lambda often from K to G. And this is just a set, and so G acts on this set in a natural way on y of g, and so we can always conjugate, because all maximal tori are conjugate, and lambda of this is contained in maximal torus, and we can say that y of g has the following form: g y of t, g inverse, where g is in g. And then it becomes nicer because y of t is a lattice. So x of t is the lattice of rational characters on t. And then we have a duality between x of t and y of t. So there is a non-degenerate pairing between x of t and y of t to the ring of integers, and this is given as follows. So we say that lambda eta is equal to r if and only if we have the following. So eta is a co-character, so eta of lambda of t is equal to t to the r for all t in k cross. And this is so this is my field. So this is well defined and extends to non-degenerate pairing. Then we can consider xq of t, which is just x of t tensor over z by the field of rationals. And similarly, we may consider xr of t, and we may in the same fashion. Then we consider yq of t and yr of t. And then by using this pairing, we can actually identify, and we identify these vector spaces, xq of t and yq of t. So we also choose W invariant. W is a Weil group, of course. So W invariant scalar product on xr of t. And then by using this scalar product, then we can define a norm. After that, we can define a squared norm or just a norm mapping on y of g, which has values in non-negative real numbers. So how do we define it? So in the following way, we say that the norm of co-character lambda is equal to this value, square root of g lambda g inverse for g where g is such that g lambda g inverse is in y of t. And so by using Briot decomposition, one can see that this is independent on the choice of g. So it's well defined. And then we have a norm mapping, which is one of the ingredients for defining optimal co-characters. And the second ingredient is the following. So now we look at the module. So let V be finite dimensional rational G module. And then by Mumford's conjecture proved by Habush, this invariant ring, the ring of G invariant regular functions on V is finitely generated by some homogeneous elements F1, Fm. Of course, M can be 0 as well in some cases. So Fi are homogeneous. And then we define the nilpotent cone or null cone of V to be the 0 locus of these homogeneous functions, F1, Fm. So if M is 0 here, then this would be just 1 point, 0. Otherwise, it's proper. Otherwise, it could be bigger, sorry. So the 0 locus or that, well, actually, it depends on G. So sometimes one also puts G here. It will change at some point. And there is a nice description which is called the Hilbert-Mumford criterion, So we say that V is G unstable if V is in this set. It's a conical Zariski closed set, and V is G semi-stable if it's not there. So so if you take so first of all let's take a co-character. So lambda is in y of g. Then, because our modulus is rational, V is going to decompose into weight spaces with respect to lambda. So it will decompose like this. I will denote this V lambda I, where V lambda I is just a weight space. All V in V such that lambda CV is equal to t to the power I V for all t in K cross. So we have such a decomposition, and for a non-zero vector in V, then we can write it as follows. So V is equal to Vk plus Vk plus 1 plus some higher terms with Vi in this homogeneous component, weight spaces. And Vk is not zero. Vk is not zero. We can always write our vector in this form, and then we put at k, we call it m lambda v. And this is the second ingredient involved in definition of optimal parabolic. So now, well, there is a Hilbert-Mumford criterion, which is a very important result, very general. And so it says that a non-zero vector V is in the null cone if and only if m lambda V is positive for at least one co-character lambda and y of g. So up to conjugacy, well, any unstable vector could be written like this, with all components indices being positive. However, there are lots of co-characters which have this property. So we say that lambda is optimal. It's optimal for V non-zero if the following holds. So if m lambda V divided by the norm of lambda is greater than or equal to m mu of V divided by the norm of mu for any non-zero mu y of g. Non-zero, which means non-trivial co-character. And it's not obvious that such things exist, but this was proved by Kempf and Rousseau. They always exist, and once you prove that they exist, they also have very nice properties. So one of the main results here is that proved by Kempf and Rousseau. It has several statements, so let me just recall that we say that lambda is primitive is primitive if lambda equal to n mu, this mu in y of g, if this implies that n is plus minus 1. So if it's indivisible in a sense. And any co-character can be made primitive by scaling down. This will not affect this quotient. So it's harmless to assume that co-character is primitive. So the theorem is, so let lambda v be the set of all optimal co-characters. So we take lambda in y of g such that lambda is optimal for v and primitive. Then the parabolic subgroup, I'll tell you what the parabolic subgroup of a co-character is. And the parabolic subgroup of lambda is equal to the parabolic subgroup of mu for all lambda mu in this set. And so, so this parabolic p of lambda depends only on v. So p of lambda depends on v only, and on the choice of this norm making, if G has many components, if G is reductive but not simple. And so I denoted P of V often. So to define P of lambda, there is a standard definition. So for lambda in y of g, we can we can also decompose the Lie algebra of our group into weight spaces because it's a rational module. So we'll decompose it into weight spaces as we did before. And then one knows that P of lambda, which is non-negative part of this gradient, is a parabolic subalgebra. So then this is g lambda I when I is bigger than or equal to 0 is parabolic subalgebra, and so we define P lambda is the parabolic subgroup. It's unique. With Lie algebra equal to this, P of lambda being this thing. I should also mention that there is a nice decomposition of P of lambda. It decomposes as a semi-direct product of the centralizer of lambda in G and the unipotent radical of P of lambda. And one can say what the Lie algebra of this is, and this is a Levy subgroup, something that we're going to use. So this is a Levy subgroup of G. So this is sort of the first statement, so that optimal parabolic is independent on the choice of optimal co-character. And we also have that this set really is just one orbit. Lambda v is equal to g lambda g inverse for where g is in P of lambda of P of v. So lambda v is just one orbit under the action of optimal parabolic for every lambda in this set. And the third property, which is useful if one is interested in nilpotent elements in some particular modules, some vectors, and one wants to compute stabilizer, then the stabilizer in G of vector V is contained in the parabolic. This follows from this uniqueness property. So this applies not just to the connected component of these groups are often disconnected, but to the whole stabilizer. So, and then Hesselink made the next step, he introduced some sort of virtual optimal co-characters. So we defined for V as before a non-zero vector in the nilpotent cone of V. We define, we can rescale this thing. Say lambda V bar is a set of 1 over m lambda V lambda, where lambda is in this set. So this is actually, it's not going to always be co-characters, but they will live in YQ of G, which is defined in a sort of natural way. So, but we can make sense even by working with these virtual co-characters. And then we write, following Hesselink, we write that V is double tilde W if and only if they have the same virtual set lambda bar V. So, and then we write V tilde W if and only if if and only if lambda GV bar is equal to lambda W for some G in the group. In the group G. So, and these are equivalence relations he proved. So these are equivalence relations on NV without 0. And the equivalence classes of the first relation are called the blades. So the equivalence classes under the first relations are called the blades. And the equivalence classes of the second relations are called Hesselink strata. Or GIT strata. So the relationship between the blades and Hesselink strata is very straightforward. To obtain a stratum, we just take G saturation of a blade. So the question is, how can we describe these equivalence relations? They stratify the null cones. So if we know things about these and can describe them, then we know the null cone, basically. Of course, in general, it's not easy to do. But say for the joint action, this was done long ago. So to describe the brace, yeah, there is one fact which is not entirely obvious, but the number of strata is finite. So the number of Hesselink strata is always finite. But of course, the number of blades is infinite. So how to determine strata? There is a very useful result which has a long history. At least theoretically, we know what they are. And so to answer this question, one can look at a theorem which is called Kerr-Van-Ness criterion. So let me state Kerr-Van-Ness criterion. This was proved for linear actions, but one can modify it, which we did in our paper, to work in for some actions which are not linear. For example, when the group acts on unipotent variety by conjugation. So there one can think of different versions. So to introduce to say what this is, one first needs to introduce certain rather funny-looking subgroup. So let's take lambda in y of g, so a non-trivial co-character. And then we know that the centralizer of lambda is a Lewis subgroup. And of course, lambda of k cross is contained in the center, so it contains in any maximal torus. Is in any maximal torus of this subgroup. So, and then, well, we take, let C1 be a maximal torus. And then lambda is in y of T1. And so we now define a subtorus of codimension 1, C1 upper lambda. It's going to be a subtorus in C1. It is generated by all mu of k cross, by all one-dimensional tori such that mu and lambda are orthogonal with respect to our scalar product, which we also have on C1. So, and then this is a subtorus of codimension 1, and then we set L perp lambda to be the connected reductive group generated by C1 lambda and the derived subgroup of our Levy, R lambda. So it's a normal reductive subgroup of this Levy subgroup, has codimension 1. Of codimension 1. What's going to be important for the rest of the talk that actually it has rank 1 less than the rank of G. So the rank will be smaller of codimension 1 in L lambda. And so the Kerr-Van-Ness criterion can be stated in terms of this subgroup. So then this was proved by Kerr-Van-Ness in characteristic 0, and then it had some sort of long history. Slowly we observed that it works also in characteristic P, but only in some graded settings. He imposed some unnecessary assumptions, but this was later removed by Tsuji, a former student of Kaneda. So now we have a completely general result which holds in all characteristics, basically with the same proof. So we take V, so let so non-zero vector V of the form Vk plus 1 plus so on, where K is M lambda V, and we assume this is bigger than or equal to 1. So the setup is sort of, we have a co-character which could be optimal, but we don't know if it's optimal or not. How can we say whether it's optimal or not? Well, and then the answer is then lambda is in lambda V if lambda is primitive, which is easy to achieve. and we have the following. So we look at V lambda k as a graded component for this minimal weight, and so we have this vector Vk, and of course it belongs here, but it should be semi-stable with respect to this smaller subgroup L per lambda, if it's semi-stable, which means the last thing can be restated as follows. So there should exist an invariant function. Of course, it's difficult to compute invariance, but at least we know there exists some under this smaller group homogeneous of positive degree. And such that f of v is not 0, of vk is not 0. So to check whether a torus a co-character is optimal, we need either to find this invariant function, or we could actually use some information coming from characteristic 0, where we know that such a function exists. And this is how it works actually. So if we show that this picture is independent of P, then we don't need to do anything here, because we would know automatically when we have such a function. And here is where Seshadri's theorem comes into play. So Seshadri proved a very nice result, which relies on Habush's proof of Mumford's conjecture. So he proved sort of absolute version of this, which means he worked over that in the framework of reductive group schemes. So since he works over that, using schemes is sort of unavoidable. So now let curly G be a reductive group scheme split over that, split over integers. So such things are given by root datum. So you need to take this torus, which is split over z, and we take one lattice x of t, we take another lattice y of t, and we take the root system and the dual root system. And there are some axioms that should hold. Once you have this, and then you have a reductive group scheme split over z. For example, all Chevalier groups can be regarded like this. So the advantage of working on this setting, we don't lose that much on one hand. For example, you could work with a Chevalier group over Z, and that would be fine. But here, the point is one can actually consider actions of this on lattices, not just on vector spaces. And then then well, so let Vz is a free module of finite rank, so it's an isomorphic to a fine space for some n, A and Z. So let this V be acted by linearly by this thing. So what does it mean? So this means it means that Vz is a module over a distribution algebra over this group scheme. And so in the case when we have a simple group, say a Chevalier group, then this is just think of constant Z form of U of G of this enveloping algebra. So this is a very nice Hopf algebra over Z, and it will act on admissible lattices in rational G modules over complex number. And this is how we get a linear action of reductive group scheme. And then, since this is a Hopf algebra, then it will act on this thing will also act on the symmetric algebra of the dual of Vz, which I will still denote like this. And so, and we may consider the invariance of this action, of this Hopf algebra actions. And these are exactly the invariance under the action of this group scheme. So we may consider the algebra of invariance. Which is just the same thing as the invariance under the action of the distribution algebra. Or if you think in terms of constant z forms, that there should be elements killed by all x alpha to the n over n factorial and so on. And that would be enough. So Seshadri proved that this is finitely generated over integer. So then Seshadri, so he proved that Z Vz G is generated as algebra over Z by some finitely generated element, F1, Fm. And not only this is true, you can base change, so then we may consider the scheme n of Vz, we may consider, so which is the maximal spectrum, well, the spec of this algebra, sorry, of the ideal scheme for these elements of 1 of n. So, so let me denote it like this. And then this is a scheme over Z, and we can base change we can base change it as follows for any algebraically closed field. And this in general is, sorry, in general this is not going to be reduced even if this was, so this is not going to be reduced, but we can consider reduced part. And from his result it follows that this is the way you recover the nilpotent cone of V, where V is just Vz tensor by our field. So, and this is honest rational G module. So what can happen, and it happens, there are many examples, you can have these invariants, and then when you reduce them mod p, the reduced coefficients mod p, they will still be invariants here, but not all invariants would be of this form. However, the variety will be the same. That's the result, really. What is that? And so now, using this, we can well, we can compute the number of nilpotent elements over finite fields and prove polynomial count properties here. So now suppose suppose our field K is Fp bar, the algebraic closure of Fp, and suppose that we have a Frobenius acting on G. So this is a Frobenius endomorphism. And so Frobenius endomorphism corresponding to FQ rational structure. So we don't want Rie groups to appear here, we want algebraic groups. So corresponding to some FQ rational structure. And then since finite fields are fields of type C1, so they, from the point of view of Galois homologies, they are trivial. And so there exists an F-stable Borel B in G, and a maximal torus and C in B as well, F stable as well. So we have these things, and therefore one can really say what F is. So then F is equal to, one can, well, in a sense, describe this F. It will be F tau L, where Q is L's power of the characteristic, and tau is a symmetry of the root system which preserves the set of roots, simple roots, pi. So, well, if the group is simple, there are very few such tau, but we assume G is reductive. There could be lots of them. So, and well, there are some conditions. I will just list one. So, so for example, x alpha of t in Steinberg notation, these are generators of unipotent root subgroups. And the Frobenius will act as follows. So it just we apply tau to alpha, and here we put c to the cube. And there are a few other properties for y of t and x of t, which should be satisfied for this f to exist. But this is the main property. Oh yes, the tau star is x on y of t, and tau x on x of t in a compatible way as well. So and then we also assume that fx on x on v are rational G module, and we want to look at rational f stable f invariant points x and v, so that it's compatible, so that we have G of v. When we apply Frobenius to this vector, then it should be gf of vf. And then we say that the action is compatible. There are lots of such actions. And so we are interested in the number of f rational points on the nilpotent variety. So we are interested in NVF. So these are all V in N of V, which are invariant under F. So this is a finite set. So using Seshadri's result and combining it with Kervan-Ness and Hesselink stratification, one can prove that there is a polynomial which counts this for all characteristics. The same coefficients are integers. And the proof goes as follows. Yeah, I think I will just outline it. So I will state the theorem. So before I can state it, I will need to define two sets. So first of all, we need this set lambda v, which will consist of certain co-characters, well, actually of pairs, because we want Hesselink strata. So we will say that this contains of pairs lambda k, such that this will count Hesselink strata, such that lambda is belong to the dual Weil chamber in y of t. T is this f-stable maximal torus in Borel, such that lambda is primitive, and we have this set V lambda k semi-stable, non-empty. This comes from the Kervan-Ness criterion. Now, when I write semi-stable with respect to this subgroup L per lambda, this should be non-empty. So this is a finite set. And then, since we are looking for Frobenius which are not necessarily split, so we introduce a smaller set, lambda v tau. These are all pairs lambda k, which are already in lambda v. And we also want that tau star lambda is equal to lambda. So co-characters which are stable under tau. And then we can, using Hesselink and plus Seshadri, then the corresponding Hesselink stratum corresponding to this data, which I will call H lambda k. So this is a Hesselink stratum associated with this. It can be described as follows. It's a G saturation of the following set. So here I will write the blade, and the blade looks like this. So first of all, we take this set lambda k, and we take semi-stable elements, and we add to this the rest. So v lambda I, where I is bigger than k. So there are finitely many things of this form that we need to count. This is sort of well, invariant theoretic data, maybe combinatorial at the end. And then the nice thing about Hesselink stratification, which I didn't tell you, that, well, the orbits, you know what the orbits are on this set. And so therefore you can compute H lambda k f, the fixed points under Frobenius, so they will be as follows. So we take the order of G by P lambda. So this is a projective variety, and we take F stable elements, the F invariants here, times the number of elements in V lambda k semi-stable, and we take F invariants again here. So this is something that we have to compute. Well, this is very easy. So here we write the number of elements in this vector space, which is going to be a vector space over finite field. So V lambda I f, where I is bigger than k. So now we need to count each of these. And so we have, and since we need to count this, so we will, well, by length theorem, we know how to compute this because this is a connected group, so it will be just the index of this finite group of Lie type, the index of parabolic in here, something that is known to be a polynomial in Q, which depends on tau. So f tau lambda, it also depends on lambda, but lambda comes from characteristic 0, so it's not going to change. So it's a polynomial in Q. And here we have a semi-stable. Since we're computing semi-stable, we just subtract nilpotent elements, which actually live here. So this set is just the following. We take all elements in this vector space, and there are this number of them. Here, n lambda k is just a dimension of this space, v lambda k. Again, this came from characteristic 0, didn't change at all. So, however, we now subtract something that we don't know. We subtract nilpotent elements in this module, and we take F invariant points. But we know this group L perp lambda has rank smaller than rank of G, so by induction we know it's a polynomial in Q with coefficients independent of P. So we know by induction that this is given by a polynomial. And here we have to multiply by Q to the power n big lambda k, n big lambda k, where n big lambda k is just the sum of dimensions of the larger graded components. I is bigger than k. And again, this came from characteristic 0, didn't change. So all these ingredients didn't change. And since the Hesselink strata by Seshadri's theorem are the same as in characteristic 0, they didn't change either. So, and then we can count everything. And at the end, we get this formula. So at the end, we will have that n vf is equal to, first of all, 1, because we didn't count 0, so 1 is just a contribution of 0, plus the sum of the data, so lambda k is in lambda v tau, which is a finite set, and it comes from characteristic 0, times these things here. So f lambda tau q, that's the size of the corresponding projective variety, the fq rational points, times q to the n lambda k minus the size of, oh, I didn't say, it is the number of elements, minus nv lambda k f for the smaller group, and times q to the power n lambda k. And so this is a polynomial in Q with coefficients independent of P. So it's a polynomial in Q with coefficients independent of P. They will depend, not all powers of Q would be allowed, because we are saying that tau is not in general trivial, so like unitary groups, they would require Q to be a square, so there are some minor restrictions on Q. But if tau is trivial, not any Q would be allowed here. There is one nice example which I would like to mention where one can compute everything. This is an example suitable for a Lie algebra course. So let's consider the case SL2. So now say, so let our group scheme be SL2. It's supposed to be bold-faced. So, and then, and then we take, let V be an admissible G module, or G prime module, where G prime is G of C, which is SL2C. And there is an admissible lattice invariant under constant Z form, and we reduce mod P. Okay, so sorry, V prime. And so we have V prime Z is admissible lattice in V, and we say that now we are in characteristic P, any characteristic, and so we just base change from C to our field K. And this is SL2K module, rational. And so the question is, how can we compute the number of nilpotent elements in this case? So following this scheme, which is in general complicated, in this case everything becomes trivial. So then, well, first of all, the G is a group of rank 1, so y of t primitive is just consists of two elements, because y of t is z, so it just has two elements, and the while group W is plus minus 1, so it will permute these two elements, and therefore we may just assume we have one element. And then V will decompose into weight space, because all admissible lattices decompose. So we will have some V minus R plus V minus 1, the weight spaces, plus V0 plus V1 plus VR. And we say that Ni is a dimension of the weight space Vi. And we will need uppercase N. This will be dimension of V minus dimension of the zero weight space divided by 2. So this number will pop in. Now we have co-character. What are Hesselink strata? Well, to see whether we have a Hesselink stratum, we need to check this group. Remember, we'll have this group L perp lambda, but this group has rank 0 now, so it's trivial because it's connected. And this so Kerr-Van-Ness criterion is very easy to satisfy. So all vectors which have non-zero projection onto the minimal component will be semi-stable automatically. And so therefore we may compute. So this is a trivial group, therefore it's very easy to check semi-stability property. And then we compute that NVF, the number of elements here will be. First we look at the largest Hesselink strata, which is here. So the largest Hesselink strata occurs when we take a vector, a sum of these, with a non-zero projection to V1. That's the largest one. So how many of these do we have? Well, we have over finite field, we have Qn1 minus 1, because the projection has to be non-zero, times Q to the power n2 plus 1 plus nr. So this is the size of the largest Hesselink strata. Well, I will leave, because there is also the G action, so these are only blades. So plus the smaller stratum, which will be, now we look at the next component with non-zero projection. And this will be Qn2 minus 1 times the rest, Qn3 plus 1, until we reach the last component, which is here. So we take non-zero elements Q and R minus 1, we count these. So since these are only blades, we counted blades, we now multiply by Q plus 1, because Q plus 1 is G by B F. So this is the number of elements here. And we didn't count the zero vector, so we should add 1 here, plus 1. And now really funny things happen. So bad things will start killing each other here. And there will be very few survivors. So we will have Q plus 1. And there will be one survivor, which is Q n1 plus nr. And the last one will be minus 1. Plus 1. So that's the number of rational points. If we continue this, and then we will get Q plus 1, Q to the n, where n is this number here, minus 1, plus 1. And so this is Q to the n plus 1 plus Q to the n minus Q. That's the number. So this number really depends only on m. Forgets almost everything. So when we compute n prime Vt, which is it's a polynomial which counts number of lines in the nilpotent cone. So this would be nv of t minus 1 divided by t minus 1. If you compute this, and you can find out that there's a nice formula, and this polynomial has non-negative coefficients always. And so we conjecture that this should always be true, that this should have non-negative coefficients. Somehow this is in the spirit of a conjecture of Katz on representations of quivers, because the picture for quivers actually is a very special case, because all modules that arise in theory of quivers, they're all admissible. In fact, they're semi-simple. And the group is just lots of, has lots of components of type A. So here. So when you apply this to the action of, to the following action, the G acts on the Lie algebra, on the dual Lie algebra, or on group by conjugation. So this requires some extra work because it's a non-linear action. Then we can prove some confirms some predictions made by George Lustig, that these properties P1, P2, P3, P4, P5 hold. And so, in fact, all these pieces, unipotent pieces, nilpotent pieces, are exactly Hesselink strata. So, but we couldn't prove that Hesselink strata are smooth in bad characteristics. So this is still open. It would be interesting. I tried to do it, but it seems well rather tricky to find a similar formula for groups of rank 2. For groups of rank 2, this is also very small. Unfortunately, it could be either SL2 or one-dimensional torus here. So there would be some more combinatorics arising, but I still believe that there could be a nice formula for these numbers, for groups of rank 2. And it would be interesting to check whether this conjecture stands after that. I don't know. There are some special cases when the group SL3, this was done by David Hilbert long ago. So SL3 K acting on polynomials in 3 variables, x, y, z, of on homogeneous polynomials of degree d. In this case, Hilbert describes what is now called Hesselink strata. It's in some books. And so I think, at least in this case, one could compute the number of rational points. Such actions sometimes occur in geometry, so they're quite known. Okay. Thanks.
In your setup, so if you're looking at, so you use this theory to give a case-free proof of the Balakata theorem for a good characteristic.
Yes, it becomes, in good characteristic, there is one extra property which is lacking in bad characteristic, the separability of orbits. Well, if you change Lie algebra slightly. And if you add separability to this, then that would be a classification of orbits. But since there is no separability in general in bad characteristics, so the Hesselink strata are not always orbits. So sometimes they're just bunches of orbits. Often they are just single orbits, but not always. Yeah. So this just is what you get from characteristic 0.
So the parabolic and Levy subgroup you associate, would these be the same as the canonical parabolic and Levy you get from the weighted Dinkin diagram?
Yes, the data is absolutely.
These always coincide in the.
Yeah, the data for Hesselink strata all comes from characteristic 0. It's not going to change. But in good characteristics, the strata will be orbits, just honest orbits. Okay. But in general, you will have just bunch of orbits which behave in a very similar way, but they are not always conjugate.
So this primitive, you had to pick a primitive character. Is this somehow like picking a
SL2?
An SL2 triple?
Yeah,
that's
it's the same
dominant
thing.
Fundamental.
Yes. So the optimal character comes from characteristic 0. It doesn't change at all.
Okay. So you're somehow just eliminating the SL2 triple from the.
Yeah. So from SL2 triple and characteristic 0, you can pick a co-character, which you can then use in any characteristic. So in any characteristic, it would be optimal.
Okay.
Yeah.
Okay.